So let's take a look at A. One of the potential tricks to this one, of course, is that position is defined as a piecewise graph. And I think I've got it set up correctly so that S is continuous even at pi. But a series of questions is going to ask you to deal with the correct piece at the right time. So part A says, what is the position of the particle at t equals 1? And so we're talking about t equals 1. So for question A, at least, we're talking about only this part of the domain, right? Because t equals 1 fits in that part. We'll ignore the other part for question A. So position of the particle at t equals 1 would simply be s of 1. And so I would use my calculator. Not really. Probably don't need to on this one, right? Essentially it comes down to 1 squared plus 1. I'm coming up with 2. So position at 1 is 2. Any questions there? Okay. Part B says find s prime of 5. So this one definitely would be calculator active. If you wanted to, you could find s prime of t first. S prime of t would be the opposite of 2 pi plus 1 times cosine of t, because we're talking about the other piece now. So then s prime of 5 will certainly be calculator time. Make sure you're in radian mode. You guys come up with an answer for this one?
Negative 2.66.
You guys agree with Johnny's answer?
Yes.
Okay, so let's talk about what this means. Negative 2.066. I suppose there's a number of ways you could do this. What would be an explanation that you would offer? Any people want to offer up what you think this would be? What's the meaning within the context of this? Go ahead, Jasmine.
At t equals 5, the particle has a negative velocity of negative 2.066.
Okay, yeah, at t equals 5, the particle has a velocity, a negative one, of course, of negative 2.066. So she's correctly identified that s prime would be a velocity, and so that's definitely right on the money. If the velocity is negative, what does that indicate about the direction of the particle?
Left.
It's probably moving left. So if you wanted to say when t equals 5, the particle is moving left at a rate of, and then you'd want to be careful with this. So let's write this one out. I'll erase this. Oops. So if I check this out, even if you feel confident, check it out. If you were to say the particle is moving left at a velocity of, if you're going to say this, you need to list it out as a 2.066 velocity. If you were to say the particle is moving left at a velocity of negative 2.066, that's actually a double negative. So if you're moving left at a negative rate, you're actually moving right. So you want to be really, really careful that you don't double negative yourself right out of credit. Absolutely will be looked at as far as explanations go. So you'd want to list something like that. And you do want to put the time. So, at t equals 5, particle is moving left at that velocity of 2.066. So watch out for double negatives. It jumps up to bite people sometimes. So just make sure that that's not you. All right. So then s double prime of 2. So it's kind of nice here. S double prime of 2 is back to that more simple function. So if I'm going to find s double prime of 2, I need to find s double prime of t first. And to find s double prime of t, I got to find s prime of t. So s prime of t is 2t plus 1. S double prime of t would just be 2. And so that just means that s double prime is always 2. Doesn't really matter what the input is, right? Doesn't matter what the time is. So then let's explain the meaning. What is the meaning of s double prime of 2? Acceleration, that's right. So when t equals 2, the acceleration is also 2. I didn't give you any units here, and if there are no units given, don't supply any. Don't make anybody up. Make any of them up. And also, don't be that person who puts the u per second squared, like units per second squared. There just aren't any units here, so don't put any. If there are units, then you'd probably be directed to put them. Okay, still doing all right? Okay, so then d is the speed increasing or decreasing when t equals 2. This is the thing we finished with last time. What are the two things we have to compare if we're trying to answer a question like this? Velocity and acceleration. And the good news is we have half of it, right? So I know that S double prime of 2 is 2. And what's the most important thing about that number for this question? It's positive, yep. We also have to find S prime of 2. We haven't found that yet. But I do know S prime of t from before. What would you guys say that S prime of 2 would be? 5, yep. And that also is positive. And since at t equals 2, both the velocity and the acceleration are positive, what could we say about the speed? It's increasing. So you could put a little explanation over here because S prime of 2 and S double prime of 2, both of those are positive. Speed is increasing. Still doing okay? All right. So then E, is the speed increasing or decreasing at t equals 5? We already know S prime of 5, don't we? Yeah, right there. So S prime of 5 is equal to negative 2.066, which is positive. And let's see here, S double prime,
It's not.
or negative. Sorry. We're making math up as we go here. It's now a positive number. No, it's negative. So then, if I'm going to find S double prime of 5, I got to do one or two things. I guess I could math 8 this. Did you guys do that? So we could go S double prime of 5. You could, I mean, it's not like it's that hard to do. It's just 2 pi plus 1 times sine of t. It's not like you really have to use math 8 here, but it might be convenient. What did you guys get for S double prime of 5? 6.62.
That's what I got.
Can you go 3 decimals?
Did I screw it up? Rats. What did I do?
I got.
Negative 6.98 something? 984? Brandon, I don't know what to tell you.
Actually, this was fine.
Negative
I'm just gonna drop your
6.984? Okay. Sorry, it happens. Hey, Brandon, if you're feeling bad, just realize I just called a negative number a positive number.
That's true.
So don't feel...
But I just called a negative number a positive number and a completely different number.
Well, the proof is we all make mistakes, right? Nobody's gotten through life with making no mistakes. So, okay. So this is kind of the counterexample to D. D, both acceleration and velocity were positive. This time, both of those are negative. Because they're the same sign, we can say, therefore, speed is still increasing. Therefore, speed is increasing. Okay, any questions? Hope this is a good review for Jaden and Jeff. Maybe not so much of a review. Are you picking it up okay? Okay. Jeff, how you doing? Good. Good, okay. Yes, ma'am. I don't know. Should be a positive right there, because when you differentiate, so like when you got to, so the derivative of this, the first derivative would be negative this times cosine t. When you do your second derivative, the derivative of cosine would be negative sine, and so this negative and the negative from that would be positive. Does that make sense?
Yeah.
Okay. Maybe also the question, a thought, concern? All right. So then you guys had an intro video regarding concavity and how that works with second derivatives and first derivatives. Smiley face thing. We did not do example number 1, did we? In the video? Okay, I didn't think so. All right, let's do example number 1. In it says, determine the open intervals on which the graph of f is concave up or down. Hey, listen up. This is where it can get tricky for people, because I'm asking you about f, but then the only thing I gave you was f double prime. So this is where you need to make those connections and realize what you need to do with the stuff I've supplied you with instead of just doing something automatically. For those that have had calculus before, I think a good tool to help you is a sign chart. A sign chart by itself is not a justification, but a sign chart could be helpful in helping you determine what's going on where. So please, this one is a little trickier than you might think. I hope it goes well for you. Try number 1, determining the open intervals where f is concave up or down.
Is this no calculator?
This is definitely no calculator. So Jaden and Jeff, a sign chart is just kind of a visual to help you get a sense of what's going on. It's hardly necessary here, but I think it could be helpful. And so check this out. A sign chart could look something like this for this one. I'm always in practice of labeling my sign chart. Hey guys, keep in mind, Jaden's trying to focus, so try to keep it down. I hope you guys hopefully you'll learn a little bit here too. The next thing I'm going to do is on my sign chart, I'm going to put the zeros of whatever it is that I'm trying to test out here. So my zeros would be -2 and +1 and +4. So what I've done here is I've created some intervals. How many intervals have I made?
4.
4 different intervals. So I need to test those intervals out. And you could do this kind of the slow way or the quick way. They both work. To do the quick way, you kind of have to know a little extra something, but you don't have to do it the quick way. You just need to test out some values. So maybe over here, you could test something out. There's a nice number right here in that interval you could test out. I don't know how you want to do this, but here's what I would do. I would try maybe -3. So f double prime of -3. There's a negative in there somewhere. How about that? There we go. And here's what I'm going to do. I'm just going to put positives and negatives. So if I plug in a -3 for x, the first factor would end up being positive or negative. It'll be negative, right? Because it'll be a negative cube. So it'll be a negative times, and then when I plug in here, plugging in a -3 will give me another negative. Sorry? I'm plugging in a -3. No? Yes?
Well, I'm just confused by the 4's on.
Because that's a 0. That's a 0 of f double
So it
prime.
doesn't matter that it bounces.
Well, now we're getting into the quick way, and you're kind of short-circuiting me. I'm doing it the slow way, and then we can do it the fast way. Then when you plug in the -3 into the final factor there, and you take it to the 4th power, what are you going to end up with? The fact that you're taking it to a 4th power means it's going to be positive. So you end up with a negative times a negative times a positive, and this will yield a positive. And then you could do another test value, like you could do a 0. You know, in that next interval, you could do like a 2 or a 3 in that interval. You could do like a 5 in that interval. Similar process, a negative times a positive, whatever it ends up being. But let's talk about what Colin is kind of getting at. There's a faster way having to do with multiplicity. So notice the multiplicity on each of those factors. For the first one, it is odd because we have it to the 3rd power. The next one is also odd because it's to the 1st power. Last one is even because it's to the 4th power. So if you have an odd multiplicity, you will get a sign change at that 0. It'll change from negative to positive or positive to negative. But if you have an even multiplicity, it will, like Colin said, it'll bounce. It will not get a sign change there. So once you get one of these signs, you can basically just fill it in. So -2 had an odd multiplicity, so it'd be negative on that interval. And 1 also has an odd, so we're going to get a sign change there. But then the 4 was even, so we will not get a sign change there. So the trick that some people will kind of trick themselves with is they'll do a little sign chart, and basically at every 0 they will sign change whatever is being tested. It's not always true, right? Sometimes you will get a sign change, other times you won't. So either use multiplicity or you can test every interval out, 3-4 times, whatever it takes to get there. Does that make sense? Okay, so then we can fill this out. We can say that f is concave up on these intervals, -∞ to -2, 1. Technically, you could just say 1 to infinity. Really? You could say 1 to 4 and 4 to infinity, but 1 to infinity would certainly cover it all. Can't really have concavity at a single point. Really has to be judged on some type of interval. So I would take either one of those. Because f double prime is positive on those intervals. And you could also say f is concave down on negative 2 to 1. Because f double prime is negative on that interval.
Would it have to be said for both, that you have to say like use both concave down in a certain interval, or could you just say f is concave down on an interval from negative 2 to 1? Because like that whole entire explanation, but without doing the top one. Because then you could just assume that the other would be concave up, or no.
Careful about assume.
Okay.
Because it could be piecewise and the other part could be linear, which has no concavity. So yeah, you do want to spell it out.
Okay.
Yeah. Good question. Josiah.
On these concavity problems, when you list the intervals, do you do the open?
Brackets or parentheses. So as far as I'm concerned, as far as the College Board is concerned, you can do either one, and they're not going to get upset about that. Say again?
Just besides the infinity, just.
Yeah, infinity has to be open, obviously. Yeah. I think you're going to find a lot of people that argue for brackets there, for closing it in on those. Then people are, so then the argument's going to be like if you bracket, say, the 1. So if you bracket the 1 and then you bracket the 1, it seems like you're almost contradicting yourself, right? You're saying, well, hey, it's concave down all the way up to 1, including 1, but then it's also concave up, including the 1. So at 1, is it both concave up and concave down, or what else is going on right there? So I tend to just put parentheses there. But you can put brackets too. You can, by the definition of concavity, and the same falls with the whole increasing, decreasing thing. People will argue, well, hey, how could it be increasing and decreasing at the same point? It's really not, because increasing and decreasing is judged between any 2 points. But then the College Board later on goes on and sort of contradicts itself, and it's like, well, is such and such increasing when t equals 2, which seems to indicate at a single point? And so because of that potential confusion and the arguments that ensue, they'll take either one. Okay. Example number 2. This is a graph this time, so if you guys would try this. This is not a graph of f or f double prime. It is a graph of f prime. So there's going to be a different set of conditions here. You can see kind of listed below. So example number 2, the graph of f prime is given below. Determine the open intervals on the graph of f. Is concave up. What in the world? It's like I edited this and didn't really fix it. So I will work on that while you guys work on this question. Ready, go. Oh, it's just. There we go, that's better. Determine the open intervals where the graph of f is concave up. What are we actually looking for here? Where the slope of what? Of that graph. Fair enough, yep. Hey guys, listen up please. So Ashley, what did you find? What intervals?
Well, it's positive from -4 to -1.
So you said it is positive from -4 to -1.
F prime has a positive slope from -4 to -1. Is increasing.
Okay, hold on. Now you're throwing different stuff out. So you said for -4 to -1, f prime is what?
Is increasing.
F prime is increasing, okay. So, but the wording you said before was actually pretty good. She said has a positive slope.
Okay.
I would take that. That's totally fine. So for that interval, f prime is increasing. Anything else you would add to that?
It's also increasing from the interval 2 to 5.
So we'll put 2 to 5 in there as well. So on that interval 2 to 5, the same characteristic applies. Therefore, f is concave up on those intervals? Is that how you'd finish that?
Yeah.
Okay, I like it. So I think Ashley's response certainly opens the door to talk about there's more than one way to do this. Like literally, if you put for those 2 intervals, f prime has a positive slope, that's actually a really nice description. That would work. That would give you full credit. That's great. But if you were to say something like, for those intervals, f prime has an increasing slope, now we are not talking about the same thing, are we? That's actually f triple prime, right? just the truth, man. That's just the truth. So you want to be super careful. And of course, the other thing I think worth talking about, at the start, Ashley used the word it, and she quickly corrected herself. If you ever start to say it is doing such and such because it is whatever, it's really confusing. I don't know what you're talking about. I'd like to think I do, but I really don't. I really don't. Okay, so then a point of inflection here is our next piece of information. Point of inflection is a location where Mr. Kirchner talks about in chapel, bad joke, but he always talks about a point of inflection, and I'm like, that's not what a point of inflection is. So it is where the blank changes. What would you put in the blank? Concavity, yep. It's where the concavity of whatever graph we're looking at changes from either concave up, concave down, or vice versa. So there's several different types of wordings that you could use here. Point of inflection for f is where f prime changes from either increasing to decreasing or decreasing to increasing, or it's where f double prime changes signs from positive to negative or negative to positive. So any one of those three would be an appropriate way to justify an inflection point. My preference would be that that you use the information that you're given, but historically, I typically am okay if you use any of those three for any given situation. Okay, a few other fill in the blanks here. To locate points of inflection, determine the values for which f double prime changes signs. We're just getting a little repetition here. Or where f double prime changes from. There you go. Or the other way around, like so. So inflection points have come up twice now, right? Both with the first derivative test as well as this whole concavity piece. Okay, there's lots of little details here, and I think I'm covering them all, but if you have a question, it feels like I've left something out, you let me know. Okay, let's see what's next. I think okay, there we go. Points of inflection. Okay, that's where we start talking about the second derivative test. All right, so if you guys would, find the points of inflection, and we'll just sort of discuss the concavity afterwards. Let's go ahead and work on example 3. I'm going to use f double prime to help me answer this question. I need to find that first. So f double prime is equal to 6x squared minus 6x minus 12. Sorry, that's f prime. Let's fix that, sorry. And then f double prime is 12x minus 6. So this is where you can get into a little bit of trouble. You might put equals 0, that's great. And then you might put x equals 1/2, also great. And you might leave it at that and say, hey, you know, that's obviously a point of inflection because f double prime equals 0. That's not necessarily true. F double prime can equal 0 and not change signs. The strict definition is that f double prime has to change signs for f to have an inflection point. And so what you'd have to do here to be sure that that actually is an inflection point is test out f double prime. So we know that f double prime is 0 when x equals 1/2. Test a value out over here just to be for sure. Maybe like f double prime of 0. You can see that that is negative 6. So it's negative. Whereas f double prime of 1 is equal to positive 6. So positive right there. So you'd say f double prime changes signs at x equals 1/2. Therefore, f has an inflection point at x equals 1/2. Okay, walking around, I saw a lot of x equals 1/2. How are you guys with justification, your wording, and all that, Colin?
So for the if test, we would have to use the f double prime of 0.
For the you said for the something test.
For like in doing this, we can't just do like. Didn't you say they don't accept the sign chart? So we
Oh,
would
right.
Say f double prime of 0 equals 6.
Yeah, they being the readers, they literally instruct us like if you see a sign chart, just pretend like it's not even there.
So we need the.
You got to do some kind of a sentence. Yep. Discussing the concavity, when you do have that sign chart, discussing the concavity actually becomes pretty easy. On what interval is f concave down? That's right, because that's where f double prime is negative. And then the right side from 1/2 to infinity, f is concave up, because f double prime is positive. So, as a discussion, there you go. Any questions? All right, so then In section 3.3, we talked about relative extrema, relatively high and low points, and we used the first derivative test to help us figure those sorts of things out. In this section, we're going to talk about the second derivative test. The second derivative test is actually not on the AP, AB, or BC curriculum framework, but it is often the better method to be used. So that's why I teach it. And sometimes if you look at the College Board grading standards, they use the second derivative test to justify stuff. So a lot of times it's easier, and so that's why it's included here. All right, so let's do this one together, example number 4. I want to run you through this, just make sure we're all good. It says, find all relative extrema. We're talking about relative mins and maxes right there. So let me just ask you guys this. What are your candidates for relative extrema? Careful, right? It's tempting to say critical points and endpoints, but it's just critical points, right? Because there are no endpoints, really. And if they wanted you to include the endpoints, they'd probably give you some, and they would not ask for relative. They would ask for global or absolute, right? So they're asking for relative, and so our only candidates are going to be critical points, critical numbers, and that's it. We don't have to worry about any endpoints at all. And so once you do find these critical numbers, we're going to talk about how you could actually figure out whether you have mins or maxes. So critical numbers are where what is happening. F prime is 0 or doesn't exist. So f prime for this would be 3x squared minus 10x plus 7. I want to know where that equals 0 / DNE. Why should I be super comfortable with that having no DNE? Yeah, no fractions. It's just a quadratic. It's a polynomial. Yeah, there's no reason to even worry about it. No way of having a 0 in any denominators or anything like that, so no worries. You're going to have to factor, and I don't know if that's a scary word or not. I hope it isn't. I know. I think we're good there, right? Okay, so then you set both factors equal to 0, and you solve. So critical points at x equals 7/3 and x equals 1. So in the past, what we would have done is we would have done this whole sign chart thing. We would have created 3 intervals and tested out each interval and seen that, hey, f prime went from negative to positive or positive to negative and drawn a conclusion from that. That's the first derivative test. Instead, I'm going to follow the directions here, and I'm going to use the second derivative test. In order to use the second derivative test, I need to find the second derivative. So here the second derivative is going to be 6x minus 10. And what do I do with this? Do you guys remember? Yep. And how do I decide the whole concave up or down thing? And what do I plug in to figure that out? That's right. You take the critical points themselves and plug them into f double prime. That's right. So I would write f double prime of 7/3 is equal to 4, which is positive. And Jasmine said this well. If f double prime of 7/3 is positive, doesn't that mean that f is concave up? So we could say, you don't have to say this line, but if you said, therefore, f is concave up at x equals 7/3, therefore, f has a relative what? Minimum at x equals 7/3. So then we do something similar with the 1, and I'm going to try to squeeze this in down here. I would say f double prime of 1, negative 4, which is, of course, negative, in spite of what I said earlier. Therefore, f is concave what? F is concave down. Therefore, f has a relative max. This is where it's really tempting to use the word it. Can you imagine if somebody would have put f double prime of 1 is negative 4, therefore it is concave down, therefore it has a relative max. That's really misusing the word it to refer to multiple different things. It's very unclear. So please do watch out for that. Okay, so that is the second derivative test. You're testing out is f double prime positive or negative, and that'll allow you to reach a conclusion based on that. Jaden.
So on the AP test or another test like that, would you want us to find like the full coordinate of the max or min or just that x equals?
Great question. Yeah, so it's pretty customary for relative extrema to just ask for at what x value. And I know this is a little bit unclear because it just says find all the relative extrema. I try to be really precise, like with what I want on a test or a quiz. I'll say at what x values. So yeah, it's pretty customary for these to just give the x coordinate. Certainly wouldn't be anything wrong, like if you had put the x and the y coordinate. Nothing wrong with that at all. Any other questions? Okay, awesome. So why don't you guys take a look at example number 5. The graph of G prime is given below. Check it out. Work on example number 5. This scenario where it's the limit as x approaching either positive infinity or negative infinity. And on a graph, what we're talking about is the extreme far right edge of the graph or the extreme left edge of the graph, right? We're going way out there, and you just keep going, right? So that's what we're talking about here. And so these limits at infinity are a really good descriptor of horizontal asymptotes. So you see some examples here that I've drawn. You can see the attempt at horizontal asymptotes there. So based on the graph on the left there, what would you guys say the limit as x approaches infinity of f of x on the left there would be? -2. Yeah, as you go to the far right edge of the graph, looks like we're cozying right up to that horizontal asymptote, -2. And then the other one, limit as x approaches negative infinity. We're going to the far left edge of the graph. 4 looks like a pretty, right? 4? 1, 2, 3, 4. Yeah, that looks fairly reasonable. And so we're looking for this behavior at the extreme ends. So we have some really basic rules that will help us work our way through these. And this is assuming that c is a constant in both cases. So if you have the limit as x approaches infinity of c over x to the r, so in other words, r is some exponent, like 2 or 3 or whatever, then that makes the denominator super huge, right? Which makes the limit approach what? 0. Same idea here with the limit as x approaches negative infinity of a constant over x to the 5 or 2 or whatever it happens to be, also 0. Okay, so the denominator gets huge, either direction, and the numerator is held constant, then you're going to be approaching a y value of 0. So this is where that pre-calc trick is super handy. In a lot of cases, it will severely shorten the effort needed, so that's a good thing in most cases. So number 1, limit as x approaches infinity, and we have this nice rational function. So I'll show you the real way to do this, and we'll talk about the pre-calc trick as well. Here's how you do this. The denominator. What is the degree of the denominator? 2, right? And we're looking at this 2 right here. And what's the degree of the numerator? It's also 2, right? Okay, so here is one of the quote unquote real ways to do this. What you do is you look at that degree of the denominator and you divide every single term by that degree of the denominator. So it'd be x squared over x squared plus 3 over x squared over 2x squared over x squared minus 1 over x squared. So all I've really done is I've multiplied this fraction by 1, right? And so I haven't changed anything, I've just changed the form. This would lead me to a slightly different looking limit here. So I'd do a bunch of canceling. I'd end up with 1 plus 3 over x squared over 2 minus 1 over x squared. And this is where that little idea with the top being held constant, denominator getting huge, comes into play. Because as x goes towards infinity, what's going to happen with this and this? Both heading towards 0, right? Because the constant is in the numerator, denominator is getting gigantic. You end up with 1 plus 0 over 2 minus 0. We end up with equals 1/2. For those that remember from last year, this would be a very L'Hopital rule scenario. Our friend, Mr. Hospital. We'll get to that later. So then, of course, the pre-calc trick is this. Do you guys remember from pre-calc that if you're looking for horizontal or slant asymptotes, if the degrees are equal, you're just looking at the ratio of the lead coefficients. So if you recognize that, you could have just looked at this and said, hey, look, degrees are equal. Ratio of the lead coefficients, 1/2, and you're done. So in a multiple choice scenario, that's all you got to do. Free response, you probably would use L'Hopital's rule, or maybe this. So using the old pre-calc trick, take a look at number 2. Number 2, the degrees are not equal. Right? The degree of the top is less than the degree of the bottom. Do you guys remember the pre-calc trick for this? This horizontal asymptote would be where? 0. So if you remember that pre-calc trick, you just go straight to equals 0. You could divide everything through by x cubed, and that would get you the same result. I'd prefer that you use the pre-calc trick, especially in a multiple choice situation. Number 3 is a little bit tougher, though. Number 3, when you were back in pre-calc, you learned that if degree top is bigger than degree of bottom, you just do long division. And that's not going to work here. Go ahead.
So what sort of work would you need to show from like what?
Yeah, great question. So I kept on saying multiple choice. If this was a multiple choice, I'd want you to do this. So for multiple choice, I'm not going to go through and look at your steps. For a free response, I would want to see you divide through by stuff, right? By x squared or x cubed. Or if you remember L'Hopital's rule, it's a little harder to navigate through that, but you could do something like that as well. Okay, so here for number 3, we can't just do long division. That would just give us the equation of the slant asymptote. So I will do the little divide by the degree trick. So it's going to be limit as x goes towards infinity. What would I divide everything through by? X to the first, right? Because the degree of the denominator is x to the first. So it'd be 3 over x minus 2x squared over x over 3x over x minus 1 over x. Divide everything through by x. And then end up with 3 over x minus 2x over 3 minus 1 over x. So now we try this infinity thing. So for the first term, 3 over x, as x gets huge, 3 over x is heading right towards 0. But the 2x, what's 2 times infinity? It's just, just a different version of infinity, right? Just a slightly bigger, I guess. I don't know. So that would actually be negative infinity over 3 minus 0. That 0 again from the whole 1 over x. So what's negative infinity divided by 3? 1/3. 1/3 of negative infinity. Unfortunately, I have to say the 3 doesn't have a chance. You're just going to end up with negative infinity there. Okay, so this is a good place to stop. We'll do number 4 as a review tomorrow, and then we'll jump into optimization. There is no intro video, I don't think, for tomorrow. So, all right. Hope you guys have a good rest of your day. Thank you.